Ryan, hello.
Hi, thank you for having me. It's good to be here.
Uh, Thank you for joining us.
Hey.
How are you doing today?
Yeah, pretty good. A little bit cold. It's quite cold in London today.
Oh,
Otherwise good.
in Kiev also we have not very good weather today, but still we are quite positive. Is it your first time at Devoxx?
Yes, it is. Yeah.
So congratulations on that.
Thank you.
You can make a wish.
I can make a wish.
Yeah.
I guess I can wish that everything goes smoothly. and
We can see your deck. Super.
okay. And is it just the deck you're seeing, not my speaker notes? Have I shared the correct?
We can see you and your deck.
Okay, just me and my deck. Good.
Yeah.
Okay. Should I get started then?
Yeah, you're all set. Go ahead.
Okay, cool. Back to my intro. So I'm going to give an introduction to DevOps for machine learning, particularly the running of the life cycle for um, uh, DevOps around machine learning. That life cycle management around machine learning is being called MLOps. So I'm going to give an introduction to MLOps coming from a DevOps perspective. It's mostly a conceptual introduction, but I'll also try to give snippets of examples along the way. So the MLOps scene is complex and it's new. It's distinct from mainstream DevOps. So we'll start by comparing MLOps to DevOps. So we can use DevOps as a kind of point of reference to start to understand MLOps. So to understand why it's so different, we need to understand how data science is different from programming. We'll find out that the difference centers on how data is used. Then we'll look at the build, deploy, monitor workflows for DevOps versus MLOps. From there, we'll be able to go deeper on particular steps in an MLOps build, deploy, monitor workflow. I'll try to explain that MLOps challenges vary by use case, and some use cases have especially advanced challenges. So we'll touch on those a little bit before wrapping up. So DevOps, as I see it, is about making that build, deploy, monitor workflow for applications as smooth as possible. It tends to focus on CI and CD and infrastructure. It also extends to the post-deployment, the monitoring stage. The workflow is a key enabler for software products. Fortunately, there's some great tools in this space that have become pretty well established across the industry. Tools like Git, Jenkins, Docker, Ansible, Prometheus, kind of old friends now of the DevOps space. The MLOps scene is in a very different place right now. There's surveys suggesting that 80, even 90% of machine learning models never make it to live. And at least part of that is due to the complexity of running machine learning in production. There's a famous paper called Hidden Technical Debt in Machine Learning Systems, and it explains about all of the effort that goes into running production-grade machine learning systems. It has a diagram shown here with boxes showing the relative size of different tasks. There's a tiny little box in the middle for ML code, and really big boxes for data collection, data processing, runtime infrastructure, and monitoring. The Linux Foundation for AI have offered some help by producing a diagram of the whole MLOps tool landscape. It's great, but it has loads of tools in loads of sections, and even the section titles won't make much sense for newcomers to MLOps. So let's try to understand more about the fundamentals of MLOps and where it's coming from. Fundamentally, MLOps is different from DevOps because machine learning is different from programming. Traditional programming codifies rules explicitly, rules that say how to respond to inputs. Machine learning does not codify explicitly. Instead, rules are set indirectly by capturing patterns from data and reapplying the extracted patterns to new input data. This makes machine learning more applicable to problems that center on data, especially focused numerical problems. So with traditional software, we've got applications that respond directly to user inputs, such as terminal systems or GUI-based systems. You code these by starting with the hello world and adding more control structures on top of the hello world. Data science problems fall into classification problems and regression problems. Classification problems put data into categories. An example would be, is this image a cat or not a cat? Regression problems look for a numerical output. For example, predicting sales revenue from how advertising spend is directed. The hello world of data science is MNIST, which is a dataset of handwritten digits, and the problem is to categorize each handwritten sample correctly as the number that it represents. When I think of machine learning as capturing patterns from data, I think about fitting for regression problems. You basically have data points on a graph, and you draw a line through the data points and try to get the line as close to as many of the data points as possible. The distance from each data point to the line is called the error, and you keep adjusting the equation of the line to minimize the total error. The coefficients of the equation of the line corresponds to the weights of a machine learning model, and you then use that to make predictions. Of course, the machine learning training process is more complex than the way I'm explaining it. For example, there's more to the process of adjusting weights to try to get the line to fit the data. It's done programmatically by using an algorithm called gradient descent. Essentially, we randomly pick a way to shift the line, but it's only pseudo-random, as it will take a step in a given direction and then check whether that reduced the error before deciding whether to keep going that way. That step size can be tweaked, and you can get different results depending on the tweaking, so the overall process is tunable. It's okay if some of this feels like it's over your head, or even if it's old news to you. The key point that I'm driving at here is just that building machine learning models is a numerical process, and that it's tunable and an exploratory process. So basically, data scientists are looking for patterns in data and trying to find which methods are best for capturing those patterns in models. This is a very exploratory process, and the tools that data scientists use reflect this. Jupyter Notebooks, for example, are great for playing around with slices of data and visualizing patterns. So these differences between programming and machine learning have implications for how we can best build, deploy, and run machine learning systems. So let's get into more detail about how different these build, deploy, monitor journeys are. Let's go on an imaginary development journey. We can start with a user story. Let's say we're building a calculator, and our user story says that our users want to put numerical operations into a screen so that they don't have to work out the answers. We could write a Java program to satisfy the story, compile it, and distribute it as a binary. But this is 2020, so more likely we'll package the code to run as a web server that users will interact with via a browser. Most likely we'll Dockerize the web app and run it on some cloud infrastructure. Probably we'll keep the code in Git, and we'll build a Docker image and push it from CI system like Jenkins. So now let's think of a machine learning build journey. This is more likely to start with some data, maybe a question. Let's say we've got data about employees and their experience and skills and salaries, and we want to see whether we could use it to benchmark salaries for other employees during a pay review. Let's assume the data is already available and clean, though this is a pretty big assumption. But let's assume we've got good data and we can create a regression model that maps employee experience to pay, maybe using scikit-learn. So we train the model, and then it can be used to make a prediction for any given employee what the salary benchmark would be. Let's say we've given our predictions for a particular set of employees to the business, and they're happy with that. So happy they want to use it again next year, or more regularly. Then our situation changes, because then what we want isn't just a prediction, but a predict function. That'll help us because we might not want to have to rerun the training process every time the business has some new employees to check. This problem would be magnified if another department says that they want predictions too. Actually, that would add extra complication, as even if we know that the patterns from our training data are applicable to our department, we don't necessarily know about the new department. Let's assume that it is applicable. Then our main problem is a problem of scaling. How do we make all these predictions without burning ourselves out? Probably we'll use the model in a web app, so maybe we'll add a REST API around our Python code and look to run it as a web application. We might naturally package it in a Docker container, like we would for a traditional web app. This is a valid and common approach, but it's just one approach with machine learning deployment. It does present a challenge about how to Dockerize the predict function without including the training data in the Docker image. So it's also common to separate the model from the data by taking the Python variable for the model predictor and serializing that to a file using Python serialization. Then the file can be loaded into another running Python application. So if we load the model into a suitable Python web server app, then we can serve predictions that way. This varies a little from framework to framework and can vary quite a lot if the language is not Python. But basically, this is a good picture for the machine learning cycle. Get data, clean it, experiment with it, train a model, package the model into something that can serve predictions. And there are tools that are pitched each stage of this cycle. For data storage and prep, there's tools like S3 and Hadoop. Training can use a lot of compute resource and take a long time. So there's tools that help with long-running training jobs, and also tools for tracking all the operations performed during training. There are tools specifically aimed at helping make batch predictions on a regular cycle, say for just getting predictions every month or whatever the cycle is that the business worked to. Or if the predictions could be needed at any time, then there's tools for serving real-time predictions using a REST API. Some real-time serving tools are specific to the framework, and some are more general. I personally work on Seldon, which is a framework-agnostic open source serving tool. The Seldon team also collaborates on another tool called KF Serving. Both of these are part of the Kubeflow ecosystem, which is an end-to-end platform. That's another space of tools. End-to-end platforms that try to join up the whole journey. Platforms can save you the effort of stitching several different tools together, but platforms can also be opinionated, so they don't necessarily fit every use case. I'm listing these types of tools because I think it helps to divide up the machine learning lifecycle into data prep, training, and serving. This helps us make sense of the landscape of MLOps tools out there, as we can then put them into categories mapped to the lifecycle. There's also the monitoring part of the lifecycle, but we'll get to that later in this presentation. For now, the key point is that MLOps is different from DevOps, mostly because of the role of data. In particular, models are built by extracting patterns from data using code, so the training data is a key part of the model. The training data volumes can be large, and that leads to complexity in storing and processing the data, which there's specialized tools to help with. You also get different toolkits for building machine learning models, which results in models of different formats and adds some complexity to the space of tools for getting predictions out of models. space called serving. So the complexity of the way the ML build, deploy, monitor lifecycle uses data has knock-on effects to the tool landscape. We've not talked about the post-deployment stage yet, but there's also complexity there. For example, you can sometimes need to retrain your running model, not because of any bugs in it, but because the data coming in from the outside world changes. Think, for example, of how fashion is seasonal. Let's say you've got a model trained to recommend clothes for an online fashion store, and you trained it based on purchases made in the winter. Then it might perform great in the winter and make lots of money, but when it comes to summer, it's still going to be recommending coats when people are looking for summer clothes. So you would need to be regularly updating this model with new data and ideally checking that it's leading to sales. That's a complexity you don't normally get with traditional software. These complexities about handling data, they ripple through the whole MLOps lifecycle. We've talked about this at a high level so far, but now let's think about the individual steps of the workflow and the tools used in those. Let's just remind ourselves of the workflow steps with traditional DevOps. We start with a user story, specifically specifying a business need. From that, a developer will write code and submit a pull request. Hopefully, tests will run automatically on the pull request. Somebody will review it, and it'll get merged to master. There, our pipeline will build a new version of the app and deploy that to a test environment. Perhaps further tests will be run, and it'll get promoted to the next environment where there might be more deeper tests, and then on to production. In production, we'll monitor for anything going wrong, probably in the form of stack traces or error codes. The pipeline producing these builds and running the tests will most likely be a CI system, like Jenkins. The driver for the pipeline will most likely be a code change in Git, and the artifact we're promoting will probably be an executable inside the Docker image. ML workflows are different. The driver for automation might be a code change, or it might be new data. And the data probably won't be in Git, as Git isn't a great store for data, not data getting into the gigabytes. The workflows are more experimental and data-driven. You start with a dataset, and you need to experiment to find usable patterns in the dataset that can be captured in a model. When you've got a model, then it might not be enough to just check for pass-fail conditions and monitor for errors like you would with traditional software. You likely have to check how well it performs against the data in numerical terms. There can be quite a bit of variation with ML workflows. One major point of variation is whether the model is trained offline or online. With online learning, a model is constantly being updated by adjusting itself through each new data point that it sees. So every prediction it makes also adjusts the model. Whereas with offline learning, the training is done separately from prediction. You train the model and deploy it, and when you want to update the model, you need to train a new one. We have to pick somewhere to focus, and offline learning is probably the more common case. So let's focus on offline learning. As we've talked about already, a ML workflow starts with data. It can be very large and typically needs to be cleaned and processed. A slice of that data can be taken that a data scientist can work with locally to explore the data on their own machine. When the data scientist has started to make some progress, then they might move on to a hosted training environment to run some longer running experiments on a larger sample of the data. There will likely be collaboration with other data scientists, most likely using Jupyter notebooks. The artifact produced will be a model, commonly model that is pickled or serialized to a file. That model can be integrated into a running app to serve real-time predictions through HTTP. There will probably be a consumer of those predictions, which may be another app, perhaps a traditional web app. So you may need to integration test the served model against the consumer. And when you roll out the model to production, you'll want to monitor the model by picking some metrics that represent how well it's performing against the live data. The rollout and monitoring phases of the workflow can be linked. An example might help to understand this. Say we've got an online store. With e-commerce, a common way to roll out new versions of a model is an A/B test. With an A/B test, you'd have a live version that's already running, and that's called the control. And then you run other versions alongside it. Let's call them version A and version B. So we're running 3 versions of the model in parallel, each trained a bit differently, to see which gives the best results. We can do that by splitting the traffic between the versions, and to minimize risk, we'd send most of the traffic to the control version. A subset of the traffic will go to A, and a subset to B. And we'll run that splitting process for a while until we've got a statistically significant sample. Let's say that variation A has the highest conversion rate, so a proportion of its recommendations, or a higher portion of its recommendations, are leading to sales. That's a useful metric, and it might be enough for us to choose variation A. But it may not be the only metric. These situations can get complex. For example, it might be that Model A is recommending controversial products. So some customers really like the recommendations and they buy the products, but other customers are really put off and they just go to a different website when they see them. So there are trade-offs to consider, and monitoring can need more than one metric, depending on the use case. We're seeing that MLOps is complex, and in many organizations right now, the complexity is enhanced by challenges from organizational silos. You can find data scientists that work just in a world of Jupyter notebooks and model accuracy on training data. Then that gets handed over to a traditional DevOps team with the expectation that they'll be able to take this and build it into a production system. Without the proper context, the traditional DevOps team is likely to look at these notebooks and just be very confused about what all this stuff is. In a more mature setup, you might have better understood handoffs. For example, you might have data engineers who deal with obtaining the data and getting it into the right state for the data scientists. Once the data is ready for the data scientists, then they can take over and build the models. And from there, data science will have an understood handoff to ML engineers. And the ML engineers might still be a DevOps team, but a DevOps team that knows about the context of this particular machine learning application and knows how to run it in production. This is new territory. There are special challenges for MLOps that are not a normal part of DevOps, at least not right now. Now that we've got a high-level understanding of where MLOps is coming from, we can next go into more detail on particular MLOps topics. So let's take these in order and go first into training, then serving, and finally rollout and monitoring. So there's tools that are pitched particularly at the training space. To name a few examples, there's Kubeflow pipelines, MLflow, Polyaxon. These are all about making it easy to run long-running training jobs on a hosted environment. Typically, that means providing some manifest that specifies which steps to be done and in which order. That's a manifest for a training pipeline. As an example, a pipeline might have as its first step an action to download data from wherever it's stored. Then it gets split into training and validation data. The training data will then be used to train a model, and the validation data will be used as a check on the quality of the model's predictions. When we check the quality of the predictions, we'll want to record those checks somewhere. Have an automator to decide whether we should consider this a good model or not. If it's a good model, then we'll probably want to serialize it so that the serialized This is probably sounding rather like continuous integration pipelines. It is similar, but also different. The difference can be seen in the specialized tools dedicated to training. One tool for handling training, for example, is Kubeflow pipelines. It's part of the Kubeflow end-to-end platform. It's just one part of the platform, but I'm not going to talk about all of Kubeflow here, just pipelines. In Kubeflow pipelines, you define the steps for the pipeline and also visualize it and watch its progress and see any steps that fail. But the pipelines aren't only called pipelines. They're also called experiments, and they're parameterized. So there's options in the pipelines UI where you can enter parameters. Remember, I mentioned before that there can be tunable parameters in the training process, such as the step size. So you can kick off runs in parallel of the same pipeline, but using different parameters to see which parameters might result in the best model. Kubeflow pipelines is not alone in having this idea of being able to kick off runs of an experiment with different parameters. The terminology of experiments, runs, and pipelines are pretty common, and the various tools have fairly similar interfaces. These tools are intended just for the training part of the build, deploy, monitor workflow. So there's similarity here with traditional CI systems, as the training platforms execute a series of steps and an artifact gets built. But it's different, as you've also got this idea of running experiments with different parameters to see which is best. That means you have to have a definition of which is good, which is the best model. Whereas traditionally with continuous integration, you would just be building from master, and if it passes the tests, then you're good to promote. But so long as you can automate which counts as the best model, then your training can build an artifact for promotion, much like with CI. And sometimes these training systems have integrations available to CI systems. So let's say we've got a way of building our model and we want Next to be able to serve it. So we want to be able to make predictions available in real time via HTTP, perhaps using a REST API. We might use a serving solution, as there's a range of them out there. Some that are particular to a machine learning toolkit, such as TensorFlow serving, that's for TensorFlow, or TorchServe for PyTorch. There's also serving solutions provided by cloud providers, as well as some that are more general and toolkit agnostic. Some are open source offerings, such as the one that I work on, Seldon. Typically, serving solutions use the idea of a model being packaged and hosted, perhaps in a storage bucket or a disk location. And that's so that the serving solution can then obtain that model and run it. Serving solutions often come with support for rollout and some support for monitoring as well. These different aspects are integrated. As an example of a serving solution, I'll explain the concept behind Seldon and how it's used. Seldon is aimed in particular at serving on Kubernetes, and models are served by creating a Kubernetes custom resource. The manifest is designed to make it simple to plug in a URI to a storage bucket containing a serialized model. So at a minimum, you can just put in the URI to the storage bucket and specify which toolkit was used to build the model. Then you submit that manifest to Kubernetes, and it will create the lower level Kubernetes resources necessary to expose an API and serve the model's HTTP traffic. There's also a Docker option to serve a model from a custom image. I'm emphasizing the serialized models in this talk, mostly because it's common to see that with serving solutions, and it's not very common outside of the MLOps. The serving stage links into rollout and monitoring. I've talked a little bit already about the A/B test rollout strategy. With that strategy, the traffic during the rollout is split between different versions. And you monitor that over a period of time until you've got enough data to be able to decide which is best. There's a more simple rollout strategy, which also involves splitting the traffic between different versions. That's the canary strategy. With canaries, you split traffic between the live version of your model and a new version that you're evaluating. But typically with a canary, you just have one new model, and you evaluate over a short period of time than with the A/B test. It's more of a sanity check than an in-depth evaluation, and you just promote if everything looks okay. Another strategy is shadowing. With shadowing, all of the traffic goes to both the new and the old model. But it's only the responses from the older model, the live model's responses, that are used and which go back to the consumer. The new model is called the shadow version, and its responses are just stored. They don't go back to any live consumers. The reason for doing this is to monitor the shadow and compare it against the live version. So it makes sense to be storing the shadow's output for later evaluation. Now, serving solutions have support for rollout strategies. In the case of Seldon, for example, you can create a Kubernetes manifest with two sections, one for the main model and one for the canary. The traffic then will automatically be split between these two models. By default, Seldon will split traffic evenly between the models in a manifest, but you can set a field against each model called traffic. That field takes a numerical percentage that tells Seldon how much of the traffic each model should get. These rollout strategies involve gathering metrics on running models. With Seldon, there's out-of-the-box integration available for Prometheus, and some Grafana dashboards are available. These cover general metrics like frequency of requests and the latency. You also want to monitor for metrics that are specific to your use case. And there's defined interfaces for capturing extra metrics that can be exposed in the usual Prometheus way. And we have some new integrations as well that make it easier to get metrics specific to machine learning, like model accuracy. I mentioned earlier that in the shadow use case, you might want to be recording the predictions so that the shadow predictions are can be compared against the predictions made by the live model. This can be handled through logging all of the requests and the responses to a database. There are other use cases as well where recording all predictions can be useful. For example, if you're working in a compliance-heavy industry and an auditor requires to know of every prediction what the prediction was that was made. In the shadow use case, you'd use it to run queries against the data and compare the shadow's performance against that of the live model. In the case of Seldon, the out-of-the-box integration is a way to asynchronously log everything to Elasticsearch, so that everything can be made available for running queries later on, but without slowing down the request path of the live models. Now that we know a bit more about MLOps, we can delve a little bit into some of the advanced use cases. In particular, I'm going to talk about three situations which relate to serving and monitoring. First, what if the requests that come from my consumers are too messy for my machine learning model to deal with? For example, maybe we've got text requests that are not clean and require transformation before the model can give a prediction on them. This can happen with text processing use cases because often text in its raw form isn't suitable for a machine learning model. The data has to be transformed in order to train the model. So typically the raw data has to be transformed for real time prediction in much the same way that it was transformed during training. That's the raw form of the model, that's the raw form of the data, then likely that transformation is going to have to be done because the model requires the transformed form. One way to handle this is to ask your consumer application to do it, but likely the consumer application won't know much about how to do this. So you likely have to write code that will do this. Actually, you have to write that code for your training pipeline anyway. So it's good if you can build components that you could reuse. With Seldon, we have an idea of an inference graph. The graph can be a kind of pipeline of steps, where each step is a Docker container, which can be specified by plugging a custom image into the Kubernetes manifest. Seldon then orchestrates the request to go through each of the containers in the graph in order before the responses go back to the consumer. The inference graph concept also relates to other use cases. One interesting use case is where you want to split the traffic between different models, but not for the purpose of choosing which one to use. You might do this because you know the data is changing over time, and which is the best model can hence change over time. In that case, you use an algorithm to split the traffic. Multi-armed bandit algorithms typically send most of the traffic to the model that's currently performing the best, but give a small amount of the traffic to other models too. That's so that it can keep checking each of those versions in case one starts to do better. This naturally requires a concept of which is doing best, some way of getting feedback from the consumer for how good each prediction was. There are ways to provide feedback to models served with Seldon, and there are examples of multi-armed bandit components in the Seldon Git repo. There's also some advanced monitoring use cases that relate to the data that's coming into the live model and how well it matches to the training data. If the live data doesn't fall within the distribution of the training data, then you can't be sure that your model will perform well on that data. Your model is based on the patterns from the training data. So data that doesn't fit that distribution might have different patterns. One thing we can do about this is to send all of the request data through to detector components. Those detector components will look for anything that might be going wrong, so that we can flag those predictions if we need to. So let's drill a little bit further into what we might need to detect. One thing we might need to detect is an outlier. This is when there's the occasional data point which is significantly outside of the training data distribution, even though most of the data does fall within the distribution. Sometimes models express their predictions using a score. So, for example, classifiers often give a probability of how likely a data point is to be of a certain class within the model. You might expect to get a low probability on everything. Unfortunately, it doesn't work that way, and for outliers, sometimes models can give very high probabilities for data points that they are getting completely wrong. This is called overconfidence. So if your live data has outliers, and your use case has high risk associated with it, with the outliers, then you might want to detect and track those outliers. Worse than the outlier case is when the whole data distribution is different from the training data. It can even start out similar to the training data and then shift over time. Think, for example, of the fashion recommendation model that was trained on data from winter, and then you continue using it into the summer. Well, as we've discussed, then it's going to be recommending coats when it should be recommending t-shirts. If you have a component that knows the distribution of the training data, then you can asynchronously feed all of the live requests into that component. And then it can keep a watch, and you can use it to set up notifications in case the distribution shifts. You could then use that notification to decide that you need to train a new version of the model using updated data. Or if you've got other metrics that let you track model performance, and they're still showing as good, then perhaps you might choose to just check those metrics more frequently while you look more closely into what's happening with the live data distribution. So another interesting thing that detectors might be applicable for is adversarial attacks. These are when manipulated data is fed to a model in order to trick the model. Think, for example, of how face recognition systems can sometimes be tricked by somebody wearing a mask. This illustration shows a model being tricked to think 7 is a 3 by producing a 7 with a small line in the middle, a kind of line that looks a bit like what the line that the 3 has. This sort of thing is a big problem in high security situations, and there are analogous attacks that have appeared for other use cases. Part of what's going on here is that somebody has manufactured data that isn't quite like the training data set. So there are ways to create detectors for that. Explainability is another advanced topic. It's less of a monitoring topic and more of an observability or visibility question, but a very interesting one. Being able to explain why a model made the prediction that it did is a data science question in itself. There's various techniques for this. One of them is called anchors, and that asks what features about the data, the input data, would need to be fixed in order for the prediction to hold. Let's say you've got an image classification use case, and your classifier has decided that a particular image is a Persian cat. Then you'll want to know what about that image makes it stand out as a Persian cat. So your explanation technique could be to find part of the image that on its own would be enough for the image to be classified as a Persian cat. For example, maybe just the nose and the eyes alone would be enough, and any image with that eye-nose region would almost always be a Persian cat. The explainability part is a data science challenge in itself, but it links into MLOps because you'll need to know what data to get explanations for and what model was being used to make the original prediction. This is clear if we think about a use case that's a bit more real. For example, if you've got a system that makes decisions on whether to approve loans. If you're denying somebody a loan, then you might want to be able to explain why you denied them the loan. So you'll want to be able to revisit exactly what was fed into the model. You'll need to know what data to get explanations for and what model was being used to make the original loan decision. I mentioned storing requests and predictions to a database earlier, and if you do that, then you can later revisit them to work out explanations. Let's say you approve or reject loans based on characteristics of the individual and a prediction of their future income. This example here is a classifier based on a widely used US Census dataset called the UCI adult dataset. The explanation here is showing that more than 90% of the time, a separated female will be classified as low income by the model. That's a pattern that it's taken from the data that it was trained on. So basically, any separated female applying for a loan would be at a disadvantage. Clearly, this is biased and unethical, and you shouldn't be using those data points. So explainability relates to the governance topic of bias, as you've got a better chance of discovering that bias if you can explain which data points are contributing most towards the decisions. So just to summarize the advanced topics here, these monitoring and prediction quality concerns are a big part of the governance problem for machine learning. Data can change from the training data, and you can then find your model making poor quality or even dangerous predictions. We've seen that with the drift and outlier cases. Or people can craft data to trick the model as an adversarial attack. We can also find that we've trained the model using data that we shouldn't have used for ethical reasons, and that opens up questions about bias and ethics. There's also a big governance question about being able to say exactly what was running and when. In traditional DevOps, it's a familiar idea that we'd want to be able to say which version of the software was running at a given point in time and what code it was built from, so that we can then delve into that code and build it again if we need to. This can be much more difficult to achieve with MLOps, as it would also require being able to get access to all the data that was used to train the model, and likely also being able to reproduce all of the transformations that were performed on the data, and the parameters that were used in the training run. And even then, there can be elements of randomness in the training process that can scupper reproducibility if you don't plan for them. So let's finish up by summarizing what we've learned. MLOps is a new terrain. ML workflows are more exploratory and data-driven than traditional DevOps workflows. MLOps enables ML workflows. It provides tools and practices for enabling training runs and experiments that are very data-intensive and which use a lot of compute resources. It provides facilities for tracking artifacts produced and operations on data during these training runs. There are MLOps tools specifically for serving machine learning models and specialized strategies for safely rolling out new models for serving in a production environment. There's also tools and approaches for monitoring models running in production environment and checking that model performance stays acceptable or at least that you find out if something does go wrong. So that's a overview of the MLOps field now, at least as I see it. Thanks very much for listening. I guess we will be ready to move to questions.
Ryan, thank you very much for your presentation.
Thank you for the
Uh,
opportunity to present.
it was awesome. Congratulations on your first talk at Devoxx.
Thank you.
Okay, I have one question to you. So, we're close to the next year, right? To the 2021. And what will you advise to software developers for 2020 first year?
Advice for software developers.
Yep.
I guess it's very tempting in the machine learning space to be saying, get into machine learning, it's the future. And I think it is the future. I mean, I think it is going to see massive growth, but the whole software space is going to see growth. Software is going to keep growing. Like it's a massive growth area. So I think the key thing for developers is to find the thing that interests you and that is best for you to focus on at this point in your career, and really go with that and make it work for you. I think that's a great New Year's resolution for any developer.
Great one. Thank you once again. I invite you to Q&A session, so you can go by the link in your email and join our Q&A session together with participants that were listening to you. And with that, I want to thank you for your presentation once again. Wish you a good day and best of luck.
Thank you.
Thanks.
Have a good day.